Okay, good evening. I don't have to introduce myself. Today's lesson is going to be on what we refer to as acids and bases. This is something you have done in the lower grades, maybe in NS at some point in time. So this is going to be a more scientific approach to what you may have been used to in the lower grades. Let me quickly add that this is also a topic that you'll be repeating in grade 12. So it's a grade 12 topic. In grade 12, you go into a bit more detail than what I'll be teaching you today and possibly the next time, because this is going to be a two-part session. And but if the foundations are laid in grade 11, the grade 12 one will be much easier because most of the things you are going to do in grade 12 would basically be a revision or a repetition of what you are going to learn today. So, like I said, today's lesson is S's and bases. Now, S's and bases are, perhaps let me put it this way, substances in nature can be grouped into three categories. We have acids, we have bases, and substances that are neither acids or bases, we refer to them as neutral substances. So acids are like the opposite of bases. Okay. And if a substance is not an acid, it is not a base, then we say it is a neutral substance. But we are not going to focus our attention on neutral substances. We are just interested in acids and bases. Now, to define an acid and a base, there are two ways of looking at it. The first one is to define it on the basis of what we call the physical properties of acids and bases. Okay. And this is what, let me see something. This is what most of you learned in the lower grades. Okay. So, one way of defining an acid is to say acids are substances that are sour in taste or sour. I don't know how you pronounce it in South Africa, but sour in taste. Okay. Bases are substances that are bitter in taste. So that's one way of defining them on the basis of their physical properties. Taste is a physical property. Then you can also define them on the basis of their effect on litmus paper. So you can say that an acid turns blue litmus paper red and a base turns red litmus paper blue. And you can also define acids and bases on the basis of the pH. We'll talk about pH in the next section. And you can say that acids have pH less than 7 and bases have pH more than 7. So these are rudimentary definitions, basic definitions. These are the definitions you learn in the lower grades. When I talk about the lower grades, I'm talking as far as your NS. You have done this at some point in time. So, when you come to grade 11, we don't really focus on these types of definition because they are not adequate. But it's good to know them, but it's not going to help you much. What is going to help you is the definition of acids and bases on the basis of what we call the chemical properties. Okay? So, on the basis of the chemical properties, we have models, two models that are used to explain what an acid is and what a base is. But before I talk about the two models, which is the Arrhenius model or the theory and the Lowry-Bronsted or Bronsted-Lowry theory, I just want to talk about something briefly here so that when I use it, you don't get confused. Now, in acid-base theorem, or talking about acids and bases, one of the familiar things or substances that you will come across is this one, this hydrogen ion. Okay? It is often referred to as a proton. Now, why is it a proton? Now, if you look at the structure of hydrogen, I have it like this. The nucleus, this is called the nucleus, and the electron is one there. Now, the most abundant form of hydrogen, that is the most abundant in terms of isotopes, is what we call the protium. This is the protium here. It has a proton, but no neutron. So when you lose one electron, this electron, if you lose that one electron, That is like hydrogen minus one electron would give you hydrogen positive. Okay? So if you lose one electron, effectively you'll be left with only the nucleus. And since the nucleus of the most abundant form of hydrogen contains a proton, only a proton, we often refer to this as a proton. So when you hear H plus is a proton, you don't get confused. You don't ask yourself, how come? Because the protons are in the nucleus. So why is this called a proton? It is called a proton because when it loses an electron, whatever is left is only the nucleus. And inside the nucleus of the most abundant form of hydrogen is a proton. It doesn't have a neutron. So you define it as a proton. Now, another familiar substance that we'll be dealing with is this one. We call it the hydronium ion. Now, even though this is what really happens, normally reactions involving acids and bases may occur in water, okay? And if it occurs in water, this H plus is very charged. It combines with hydrogen, it combines with water to form what we call the hydronium ion, this ion. So sometimes when you talk about acids, you don't talk about acids in terms of hydrogen or the proton. You don't talk about it in terms of the hydrogen ion or what I call the proton. You talk about it in terms of the hydronium ion because the hydrogen quickly attaches itself to water and then forms this. So most of what you would find, in fact, all of what you would find is this. So anytime you see H3 is the same thing as this because this one has combined with water to form that. And for those of you who might be wondering how this is formed, this is a form of what we call coordinate covalent bonding, okay, or dative bonding. Water, as you know, is a covalent compound, but then it has lone pair of electrons. So because this one has empty orbitals, it attaches itself, and that kind of a bond is called a dative covalent bond or simply a coordinate bond. So you shouldn't get confused. It's something that you have done previously. Okay, so we are going to look at the models or the theories of acids and bases. The first theory of acids and bases, or the behavior of acids and bases, was proposed by a man called Arrhenius. Okay, Arrhenius. So we call it the Arrhenius theory. Now, he suggests that, or he tries to explain acids and bases on the basis of their behavior in water. Okay, so he says an acid is a substance that produces this H plus ions or protons, but I think just make it H plus ions so that you don't get confused in aqueous solution. So this is a popular acid. This acid, when it is in water, aqueous means water. When it is dissolved in water, it separates to give you this one and this one. Okay? So substances that produce hydrogen plus ions in water or in aqueous solution, we call them acids. And to him, a base is a substance that produces OH minus or the hydroxide ion in aqueous solution. So this is a base. When you put it in aqueous solution in water, it separates to give you this one. And, oh, sorry, this is not, this is supposed to be OH minus. Okay, that's a small mistake, a typographical mistake. So you are going to have this. So this is a base. However, even though his definition was used for many years, over time, there were challenges with the definition. And the reason for the challenges, we are going to see them very soon. So basically, the reaction between an acid and a base, according to Arrhenius, will be in this format. You have an acid plus a base to produce a salt, and water. When you talk about a salt, you are not talking about what we eat at home. It's an example of a salt, but which is sodium chloride. But sodium chloride is not the only salt. Okay, so this is an acid. This is a base. When they react, you form a salt and water. This is how he conceptualized the reactions between acids and bases. Now, like I said, even though his postulates or his theory was accepted for many years, it had many challenges. and I'm going to focus on only two of the challenges. The first one is that his definition of an acid and a base require that the reaction must take place in aqueous solution. It means in water. And therefore, any reaction that doesn't take place in water, it becomes a problem. You cannot say it's an acid or a base. So this is one of the limitations. The other limitation is that there are a number of acids and bases that do not have H plus. According to his definition, every acid must have an H in it, like hydrochloric acid, sulfuric acid, and nitric acid. You see that all of them have H, hydrogen in them, okay? But we have found out that substances like carbon dioxide, sulfur trioxide, and this one, they all act as bases, even though, I mean, as acids, even though they do not have hydrogen. Okay. And then bases, ammonia and sodium carbonate, do not have OH minus, that's the hydroxide ion, even though they act as bases. For example, they contain blue litmus paper red. Okay, I mean red litmus paper, blue. That is, let me show you what I'm talking about. It means that if you have sodium carbonate, okay, sodium carbonate contain a red litmus paper blue, so it is a base. However, it doesn't have OH attached to it. If you look at this, there is no OH here. This is sodium carbonate like this, sodium carbonate. There is no OH attached to it. So his definition was limited. And as a result of that, two people independently came up with a better definition, a much broader definition of acids and bases. And according to the Bronsted-Lowry theory, they say an acid is a proton donor. Any substance that donates or gives a proton, we call it an acid. And a base is a proton acceptor. Now, these two definitions, you have to know them. In most of the questions, they ask what is Bronsted-Lowry acid, Bronsted-Lowry base. You should be able to define it. Proton donor, proton acceptor. Okay. Now, most of the questions that come with this is usually based on what we call conjugate acid-base pair. Now, according to the Bronsted-Lowry or Lowry-Bronsted theory, uh, an acid-base reaction normally involves a simultaneous donation of proton. In other words, a substance donates a proton and another one accepts it. So proton donation, proton acceptance. So this is what I'm talking about. So it says that when an acid donates a proton, the remaining ion is called a conjugate base. So you have an acid, it gives out a proton, and whatever you are left with is called a conjugate base. Okay? So look at an example of what this is. So hydrochloric acid is an acid. If it splits, it gives you this one like this. And then whatever you have left of this is called a conjugate base. So this is an acid and its conjugate base. This is also an acid. If you remove a hydrogen out of it, whatever is left is its conjugate base. So acids would always go with their conjugate bases, and they form what we call conjugate acid-base pair. Then we talk about bases. Now, a base is a substance that receives a proton acceptor, okay? And so a base, if you have a base like this, it can accept a proton, and whatever you are left with is a conjugate acid. So base, conjugate acid, acid, conjugate base. That's how you do them. So this is a base. If it accepts a hydrogen, it turns into water. So water is called the conjugate acid. So this is the base, and this is its conjugate acid. And the same principle applies with this one. This is also a base. If you add hydrogen to it, you form what we call sulfuric acid, and that is its conjugate acid. Now we're going to look at what we call the net reaction. That is when you react an acid and a base. Let's see how it's going to go. Like I said, this part is arguably the most popular question as far as grade 11 is concerned. Most of the questions, they will ask you what is the acid and what is this conjugate base. We'll answer a few questions and you see what I'm talking about in practical terms. So let's look at this. So if you have an acid and you react it with a base, whatever happens after is the conjugate base, and then this one is the conjugate acid. So let's look at this example. This is hydrochloric acid. This is ammonia. The hydrochloric acid is an acid. The ammonia is a base. The reason why it's an acid is that it can donate a proton because of the presence of hydrogen here. This hydrogen here is H plus, and then you have Cl minus, okay? So this H plus can be donated, it can be given. So if this one gives the H plus to this, the number of hydrogens becomes 4, okay? So you have NH4. And then because the hydrogen is gone, you're only left with Cl minus. So you have Cl minus. So this is called the acid, and this is the base. But this acid, whatever is left off after removing the hydrogen, becomes its conjugate base. And then this is a base. If it accepts hydrogen, whatever forms is called its conjugate acid. I know this is a bit confusing, but just take a look at it and you will see that it is not very difficult. So this is another type of acid. This is an acid and this is a base. Now, this one donates to this, okay? And then this one attaches itself here. Normally, technically speaking, we should not even include this one. This is almost like a spectator ion. This one should have been written like CH3 and then maybe COOH, okay? Plus the base like this, okay? So this one adds to this and then you form the water, okay? And whatever you are left with is CH3OO minus. But because of the presence of this, it attaches itself to it. And then you have that. So this is the acid, this is the base. Then whatever is left of the acid after you have removed the hydrogen is this conjugate base. And this one is the conjugate acid. Okay, so you have that. So these are examples of acids and their conjugate bases, a list of them. You have to go through them and get familiar with them because most of the questions they ask would involve things like this. So if you have hydrochloric acid, if you remove hydrogen out of it, whatever is left with is its conjugate base. If you have nitric acid and you remove hydrogen, whatever is left with its conjugate base. So acid, conjugate base, acid, conjugate base, acid, conjugate base, like that. Whatever you remove hydrogen from it, whatever is left, whenever you move hydrogen from a substance, whatever becomes of the substance is its conjugate base. And the same thing applies to this. So you should be familiar with these examples. Now we're going to talk about types of acids. There are certain acids that can donate only one proton. We call them monoprotic acids. Okay? So it means that all of them have just one hydrogen, like one hydrogen here, one hydrogen here, and this one has this hydrogen here. We call them monoprotic acids. Then we have poly. Poly means many, two or more. Any acid that can donate two or three or simply two or more protons or hydrogen plus, we say it is polyprotic. Now, there are two types of polyprotic acids. We have what you call diprotic. Di means two. Any substance that can donate two H plus ions or two protons, we say it is diprotic. An example is sulfuric acid because of this two here. So it can give away two hydrogen plus ions or two protons. So we say it is diprotic. Okay. And this is the process involved. Now watch this. I know learners get a bit confused, so I'm going to explain this. This substance here is, let's say, let me take a sulfate here so that you see what is happening. Sulfate is that we learned how to write the formula of compounds, okay? And then attached to the sulfate are two hydrogens. We have one hydrogen plus and then another hydrogen plus. So the number of positive charges here are two. 1, 2. And the number of negative charges here are 2, 1, 2. So they balance each other. Okay. And so when you write sulfuric acid, you write it like this, SO4, because they cancel each other, they balance each other. However, when you remove one hydrogen, it means that they are, remember, this is two negative means a negative and a negative, and two positive means positive, positive. So they cancel each other. This one cancels this one cancels that. But as soon as you have SO4 2 minus, and you are left with only one hydrogen, in other words, that's lost only one hydrogen, your sulfate still has two negatives, and the only hydrogen here has a positive. So this one cancels that, and you'll be left with this, a negative. That's why you write it like this. If if sulfuric acid loses hydrogen, whatever is left of it, you write H, only one hydrogen is left. But your SO4, you put minus there because of this one. So if it loses the next hydrogen again, then you'll be left with 2 minus. That is what you have here. So you have this substance here, okay? If it loses another hydrogen, you'll be left with a sulfate like this, and that one, but this one becomes -2. So this is the process, okay? Let me do the same thing for the triprotic acid, which is one that has can donate 3 protons. So let's look at that. Again, this is the formula of a phosphate. This is phosphate is 3 minus, and there are 3 hydrogens attached to it. So this is one hydrogen positive, another hydrogen positive, and a third hydrogen positive. So in the first reaction, the first step of losing a hydrogen, you are going to have PO4. If it loses one hydrogen, okay, the number of hydrogens becomes 2 now. But your PO4 becomes minus, okay? And the reason is simple. These are 3 negative charges. 1, 2, 3. 1, 2, 3 positive. So they cancel each other. That's why you don't write any charge here. As soon as you lose one hydrogen, then you are left with 2 positive charges, but 3 negative charges. So this one cancels that, this one cancels that, and you'll be left with a negative. And this negative is what you write here. So then you write H plus. Then this one can further lose a hydrogen because it can lose 3 hydrogens. So even this one can lose another hydrogen. So we can write it like this, PO4 minus, okay? It can lose 1 hydrogen. So when it loses 1 hydrogen, it now becomes only 1. Then the PO4, we write 2 minus plus hydrogen, okay? And then this one can further lose a hydrogen because it can lose 3 hydrogens, and these are the steps in which it loses the hydrogen. This one can lose a further hydrogen. So this is HPO4, 2 minus, will break down to give you PO4. Now this one doesn't have a hydrogen, but then this one becomes 3 plus hydrogen. So you see 1 hydrogen, 1 hydrogen, 1 hydrogen. That's why you have H3PO4. These are the hydrogens that are attached to it, okay? So basically that is it. Now bases can also be monoprotic, diprotic, and polyprotic, but we shouldn't really focus on that. Normally they don't ask anything about it. I just added it for purposes of enrichment, so I don't want to confuse you. Then we are going to talk about what we call an ampholyte. Ampholyte or amphiprotic substances. An ampholyte is a substance that can act as both an acid and a base, okay? There are certain substances that can act as acids and they can also act as bases at the same time. Such substances are called ampholytes or amphiprotic substances. An example is water. Okay, so let's see how water acts as an acid. This is your water. Okay, there are two hydrogens here, so it means that it can donate at least one hydrogen. So if you remove one hydrogen from this, okay, so this is how water looks like. You can put water like H, O, and H. Okay, so if you remove one hydrogen from water, you'll be left with OH. So this OH is the one we put here. Then this hydrogen that was removed is added to ammonia here. Okay, and then the water becomes, this one is called an acid. It's acting as an acid here because it's donating a proton, it's giving a proton, and its conjugate base is this OH. Now, this one accepts the proton, and then its conjugate acid becomes this one. So basically, this is how water behaves as an acid. Now, water can also act as a base in the presence of another acid. So, for example, this is an acid, and instead of water donating to this, it accepts protons or hydrogen plus ions. So this one is added to the water, and the number of hydrogens increase. That's why you have H3 positive. And then when you strip this one of hydrogen, you'll be left with this. So this is how water acts as an acid and a base at the same time. So water is an example of an ampholyte or amphiprotic substance. But water is not the only one. These are other examples. Now, so let me give you a clue. When they ask you to list any amphiprotic substance, okay, or an ampholyte, this is the clue. Always look for water. Water is always a constant example. Okay, so I'm giving that away. The second clue that you will need to know is that in any substance that has hydrogen attached to it, whether it's one hydrogen or two hydrogens, and a charge attached to it is also amphiprotic. So, for example, this one, HSO4 minus. It has at least one hydrogen and a charge, a negative charge. So this is also an ampholyte. It can gain a hydrogen, and then in that case, it becomes sulfuric acid, H2SO4, or it can lose that hydrogen and then becomes SO4 2 minus. So in that way, it behaves as an acid and a base. So I'm saying that anytime they ask you to find out maybe in an equation which is an ampholyte or which is an amphiprotic acid or substance, water is an automatic one. It's always an example that you can consider. The other examples are any substance that has hydrogen and then something attached to it with a negative charge. So this is an amphiprotic substance. It has one hydrogen and then there's a negative charge. This is amphiprotic. It has one hydrogen and there's a negative charge. This is amphiprotic. It has one hydrogen and then two negative charges. Okay? But it is not only this, especially for this one. Even this one, H2PO41, it's also amphiprotic. It has two hydrogen. When I say it should have hydrogen, I mean at least one hydrogen atom, attached to it, okay? So it can be one, it can be two. So in this case, it's also amphiprotic because it has two hydrogens and a negative charge. So that's how you're able to identify which is an acid and which is an ampholyte or amphiprotic substance. Water is a constant. Then any other thing that has at least one hydrogen and a negative charge is also another one to consider. Now we're going to look at reactions of acids and bases. Now, acids react with metal oxides to form salts and water. So this is an acid, this is a base, this is salt and water. Now, acids also react with metal oxides to produce salts and water. So I'm using a different example here. This is an acid, this is also an acid, but I don't want to use the same acids throughout. So I'm using sulfuric acid. Copper oxide is a metal oxide. Will give you the same thing as salt and water. Now, if you react an acid and a metal carbonate, you produce salt, water, and carbon dioxide. So this is an acid, this is a carbonate, you have a salt, water, and carbon dioxide. And then if you react an acid with a metal hydrogen carbonate, they used to call them bicarbonate. So this is an acid, this is a metal hydrogen carbonate. It's not a full carbonate, it's hydrogen carbonate. You produce a salt, water, and carbon dioxide. And when you react an acid and a metal, like an acid and zinc, you produce a salt and hydrogen gas. Okay? So this is what we have as far as this is concerned. Now we're going to talk about acid-base strength. How strong is an acid and a base? Certain acids are strong, certain bases are strong, certain acids are weak, certain bases are weak. So how do we define strong acids and strong bases, and weak acids and weak bases? To understand this, we have to look at two terminologies. The first one is what we call ionization. Now, ionization is a chemical process where a covalent molecule produces ions in solution. Okay? I'm interested in this word molecule, covalent molecule. Dissociation involves ionic compounds. Okay? So ionization is covalent substances, dissociation, ionic substances. So we are going to look at this. How do we define a strong acid? You say a strong acid is a substance that completely ionizes or ionizes completely, ionize completely in solution to form a high concentration of this. If you don't want to use this, you can also just say H plus. Remember I said it is H plus, but it normally combines with water to form the hydronium. So this is the proton, but then it combines with water to form that. So this is the definition of a strong acid. So examples of strong acids include hydrochloric acid, sulfuric acid, nitric acid. So in other words, when you put it in water, almost about 99% of it changes, splits to form or to produce protons or hydronium ions. Okay, so these are the examples. However, weak acids are the opposite. They only dissociate partially. It means only a small percentage of them dissociates. So we define a weak acid as acids that ionize slightly or partially or incompletely in solution to form a low concentration of that. And these are examples of your weak acids. Have them like that. The same concept applies with bases. A strong base is one that completely dissociates in water to form a high concentration of hydroxide ions, complete, almost complete. And these are examples of your strong acids, strong bases. You have your sodium hydroxide, potassium hydroxide, and lithium hydroxide. And then the weak ones are the ones that partially dissociate. So you are going to have examples of this being ammonium hydroxide, calcium hydroxide, and magnesium hydroxide. These are the weak ones. So that is what the definitions are. I think I should go to home. Okay. So now we are going to end by looking at the difference between a concentrated acid, a dilute acid, a concentrated base, and a dilute base. When you say something is concentrated, it means that you have a lot of that thing in a small volume of water. Okay? So, for example, oh, by the way, we did concentration earlier on. Remember, we said concentration is number of moles over volume. But in practical terms, let me use, for those of you who like drinking juice, this popular one is called Oros. If you take Oros, Oros is concentrated. You cannot drink it like that. It's too sweet because it has a lot of whatever they put inside in a given volume. So you normally dilute it. It means you take a small amount of it, add water, and then it tastes better. If not, that it contains too much sugar. So the same principle applies here. We say concentration refers to the amount of acid or base dissolved in a given volume of solution. A concentrated acid or base has high amounts of an acid and base or base and a low amount of water. You understand that? So if something is concentrated, it has a high amount of whatever is inside, whether it's an acid or a base, and the amount of water is low. A dilute substance has a high amount of water and a low amount of whether it's an acid or a base. So that's how you define concentrated. Concentration has nothing to do with strong acids and bases. If a strong acids can be dilute or concentrated depending on the amount of water that you add to it. Okay, so this is very important. Now, like I usually do, we are going to end here, but before we end, we will answer some past papers. Okay, so the first one says that phosphoric acid reacts with water through the following step reaction. So you have this one with water, and then you produce that. Step 2, this with water, you produce that. Step 3. Then the question is, why is this phosphoric acid a Lowry Bronson acid? You say it is a proton donor, or it donates protons, okay? Because we say acids are proton donors and bases are proton acceptors. Then the next question says, define the term ampholyte. Define the term ampholyte. I said an ampholyte is a substance that acts as an acid and a base. So that is an ampholyte for you. Then in the next question, where's my, I can't see the case. Okay, so the next question says, identify two substances that act as ampholytes in the reaction above. Two substances. Now, as a given, I always told you this, or I told you this previously. The most obvious example of an ampholyte is water. So anytime they ask you for an ampholyte, look for water. So water is an obvious example of your ampholyte. So water is one. Water is always an ampholyte if you see it. Then any other substance that has hydrogen and a negative charge is also an ampholyte. So this is an ampholyte, okay, which is the same thing as this one. And then even this one is also an ampholyte. So the ampholytes are many. We're going to have this. It's an ampholyte, water, this H2PO4, 2, PO4 minus is an ampholyte. Then HPO4, 2 minus is also an ampholyte. So this is an ampholyte. This is also an ampholyte. You choose any two of them. Then the next question says that write down the conjugate acid base pair in step 2. So you go to step 2. This is, let me clean it so that it doesn't interfere with what I want to. So we are dealing with step 2. It says they are looking for one conjugate acid. You start with the acid and a base. So the acid must contain hydrogen here. So this is step 2. So this is the hydrogen. Okay. In this case, water could also be, but if you look here, you see that the water has, the number of hydrogens in the water has increased. So the water is the one that is accepted. So this one is the acid. So your acid is going to be H2PO4 minus, and its conjugate base pair. It means that when you remove that hydrogen, whatever was left is its conjugate base. So this is the conjugate base. So this is going to be this and HPO4 2 minus. So that is for this one, okay? Then This one says complete and balance the following reactions. Yeah, this we did it before. It's in the notes. This is H3, COO, and then your Na, sodium attaches to it, plus water. So this is already balanced. Okay. And then this one is you're going to exchange them. You're going to have calcium chloride. So this one goes here. We exchange them. So that's calcium chloride plus water plus carbon dioxide. Okay. Remember, acids reacts with carbonates to give you water, a salt, water, and carbon dioxide. Let me go back and show you what I'm talking about. I said, yeah, this reaction. Acids plus metal carbonates. So an acid plus a carbonate will give you a salt, water, and carbon dioxide. So here, excuse me. Yeah. So here, this is our salt, which is calcium carbonate, calcium chloride here, and then water and your carbon dioxide. Okay. Then we balance it. We put 2 here so that this one is balanced. Okay. Yeah. So basically, that is how it should be done. So we are finished with it. Now we come to the next question. This one says that when sulfuric acid reacts with water, it ionizes in 2 steps, as shown in the 2 balanced equations. So you have the 2 equations. Give the Lowry-Bronsted definition of an acid. You say an acid is a proton donor. Okay? Proton donor, you get 2 marks. Then the second question says that write down the formula of the conjugate acid of this. It means this is a base. Remember, I said this is an example of an ampholyte. An ampholyte can exhibit or act as both an acid and a base. And the most obvious way of identifying ampholytes is that the substance must have hydrogen, at least one hydrogen, and then a charge, a negative charge. So if they say that write down the formula of the conjugate acid, it means this is a base. Okay. This one is going to be a base. Then we look for the conjugate acid. So you come back here and look for this one here. Okay. So that is this one. So this is, say, write down the formula of the conjugate acid of this one. Okay. Which one is giving you that? So that is the water. Okay. Take that confusing it. Let me check this question again. Let me erase this and then look at how it is done. Okay. It says write down the formula of the conjugate acid of this. So if this is an acid, let's say HSO4. Okay. The acid of this one is this one. Okay. Because this one is the one that donated hydrogen. And then eventually you got this. So this is the conjugate acid of this one. And this is the product. So this one is this one is H2SO4. Is what you're writing. And then the conjugate base of this. So it means this is an acid. And what is its conjugate base? This is the acid. And its conjugate base is this one. So this is what you're going to write here. SO4 2 minus. Then which one of the compounds in reaction this and this is an ampholyte? Because they said which one of the compounds? Ampholytes, I said Water is obviously always an ampholyte, so water is one example. And then anyone that has hydrogen and a charge attached to it, a negative charge, not a positive charge. So this is also an example. So here you have two, you choose one of them. You have water or your HSO4 minus. So you choose any one of them. Then we come to, okay, come to this one. Okay, this one says that define an acid in terms of the Bronsted-Lowry theory or Lowry-Bronsted theory. So you say an acid is a proton donor. So an acid is a proton donor. Now this one says consider the following acid-base reactions. You have this kind of reactions here. And it says identify the conjugate acid-base pairs in the above reaction. Okay. So if you look here, this is obviously an acid. There's a negative sign here. You might not see it well. Okay. It donates a hydrogen to this. So this is the acid and its conjugate base is this one. What remains of it after it has lost its hydrogen is that. So here you are going to have your acid as H2PO4 minus acid, and its conjugate base is HP2 minus. And then this one is also another pair between this one and this one, but it's a base and an acid. So you can also have NH4 plus an acid, and its base will be, that is if you reverse it, would be NH3. So these are the pairs, acid and its conjugate base. This is an acid because it's capable of donating hydrogen, and whatever is left with is the conjugate base, acid conjugate base. So these are the two. Remember the marks indicated there is 4. So I think this one will be 1, 2, and this will be 3, 4. Then define an ampholyte. An ampholyte is a substance that acts as both acid and base, or can act as an acid and a base. So choose an ampholyte in this reaction. So, but there are two ampholytes here. The first one is your HPO4 minus H2. The first one here is an ampholyte. Why? Because it contains at least one hydrogen and a negative charge. This one has 2 hydrogens. So that is an ampholyte. Then the other ampholyte is this one. It has at least one hydrogen and then a charge here, 2 minus. So these are the 2 ampholytes. Okay, can act as an acid and a base. So that is what we are talking about. And then we are going to finish with this one. Let me send a message and then okay. So this one says ammonia can readily dissolve in water according to the equation below. So you have the equation below. Explain why a hydroxide ion is regarded as a Lowry-Bronsted base. A Bronsted base is a proton acceptor. So you say because it accepts protons, or a proton, accepts proton. Acids are proton donors, bases are proton acceptors. So this one can accept a proton, so it is a base. Then identify the type of bond responsible for the formation of the ammonium ion in the above reaction. I say this one is a coordinate covalent bond. Coordinate covalent bond. We can say dative covalent bond. Okay? Dative covalent bond. And then the last one says, write a balanced equation to show how the ampholyte in the above equation will act as a base when it reacts with hydrochloric acid. So like I said, the ampholyte, the obvious ampholyte is water. So water is always an ampholyte. So the ampholyte here is water. Now, if water reacts with hydrochloric acid, how will the reaction be? So you have hydrochloric acid plus water, okay? Will act as a base. So a base means it is accepting hydrogen, a proton acceptor. So this hydrogen must come here. So you're going to have something like this, H3 plus, okay. Maybe if you don't want, let's do it in order so that you don't get confused. We started with this one. So when you lose hydrogen out of hydrochloric acid, you are left with Cl minus, okay? Plus whatever is added to this increases the number of hydrogens to 3, and then you have something like this. So you write here aqueous, and these ones you can just write them as a liquid and aqueous. And that brings us to the end of it. But even if you don't write the aqueous, I think you would still be given marks for that. So this brings us to the end of the lesson. We'll continue the next session later.